picture and my own face here, which is enough to scare the daylights out of anybody.
Okay, Jack. We'll talk to you later. Take care, Jack.
All right. Yeah, it seems like everybody else on the planet has dropped off. Hello, no audio. I'm not hearing anybody out there.
Can you hear me now?
Yeah.
Yes.
Yeah.
All right, let me get this on here.
You have come to life. Yes, good.
Okay, is that a good spot? Everyone can hear this all right?
Yep.
Okay.
Is Spencer ready to record?
It's already going. It's already going.
Everybody get one?
Well, hi, everybody. Welcome into the November 11th Los Angeles Astronomical Society General Meeting. Welcome, everybody. Do we have any new members tonight? Here? In-house? Oh, we've got two. Up there in the back, who's this?
I'm Sean Kenny.
Sean Kenny. Well, hold on, no, we're going to get you, Mike. Just tell us a little bit. Oop, take the whole thing. Tell us a little bit about how did you find us? Why are you here? What do you want from us?
Lights, interrogation.
Remember, everyone, if you don't speak to the microphone, the people on Zoom cannot hear us. So just a quick intro, who you are, blah, blah, blah.
I'm Sean Kenny. I'm very much an amateur and new to this, but I have been volunteering up at Mount Wilson, and you'll probably see me next weekend and next season as the guy who sells merchandise at the cafe.
Oh, okay, cool.
Thank you very much.
Hands here. Awesome.
And we had somebody here in the middle,
Where's the other person? Aha.
new member right here.
Yeah.
He's coming with the microphone.
Here you go.
So how did you find us? Did you tell us how you found us back there?
Mount Wilson.
Mount Wilson, okay.
Just by everybody else at Mount Wilson.
Got it, okay.
I'm Alan Abrams. I came back to haunt you. I was a teenage member in the 50s here, and born and raised in LA, moved all over, but I belong to the Ventura County Astronomical Society, and I wanted to come back and see what's alive and kicking here, and since I'm retired, I've got more time.
So do you live there or here?
Yeah, I live in Thousand Oaks, and
Halfway.
I've been an active amateur on and off, mostly off because of academia and family and life, but I'm a very avid observer when I get the opportunity.
Well, glad to have you back.
Thank you.
Is there any new members online? Doesn't look so. I think I know. Do I know everybody there? Okay, so no.
You can see the Zoom right on
Oh, right there. That's easier. Thanks, Evan. I got a couple of announcements of upcoming dates of things. First of all, next Wednesday. Who's talking here? Hey, hello? I have started. Okay, so starting this Wednesday and every Wednesday, remember that Garvey Ranch Park is open. It's got a nice refractor telescope there. People hang out. If you don't know what to do with the telescope, bring it there. Got great help. Loaner programs run out of there. Good place. Every Wednesday, 7 to 10 p.m. Come and have fun. Let's see. November 18th is the next Griffith Star Party here, and it's the Palomar tour for LAAS members who've signed up for it so far, which is quite a number. So conflicting events, but we'll see how that goes. Let's see. After that, December 9th is our last dark sky night at Garvey. Bring your snowshoes. If you can even get there. Always check conditions. I'm sorry, Lockwood. What did I say? Did I say Garvey?
Garvey.
Stuck on Garvey. I meant Lockwood. There's no dark sky in Garvey ever.
We should do it.
Yeah, we're working on that. Okay. And then the next general meeting here, and the last meeting is December 11th. And I have December 16th as the last Griffith Star Party of the year here. Other than that, I don't think I have any other big announcements.
Yes, elections.
Elections at tonight
No, you can tell them what's coming up.
in December. So when do the nominations are open?
Nominations are open tonight if somebody wants to nominate, and the election is by the December meeting, but Spencer's gonna send out an email ballot and.
You should say that in the microphone.
Oh, okay. I'm sorry. I'll kind of repeat that. So Spencer's going to be sending out an email, or let Tim. Go ahead, Tim.
Oh, boy.
Yes. So
Okay.
I'm also going to post I'll also post the link for the nominations in the chat in just a second or two.
Okay, so the idea is you can nominate somebody tonight if you want to, or sneak in a nomination before the election. Spencer will send out an election link, and we'll read off the results at the December meeting rather than holding the election during the December meeting as we used to do. And of course, December is the show and tell night meeting, so our own members are the speakers for the December meeting. So if you've done something really, really exciting or incredibly boring, I don't care, bring it in December and then share it with everybody else so we can be equally excited or bored or whatever.
Okay.
Last thing is
And
the banquet.
yes, we
Have it.
do have the annual banquet coming up. I don't think the announcement's been mailed out yet, but I'll pick on that again tomorrow and get it mailed out. January 28th, a Sunday, at the Quiet Cannon, and I think $75. They raised the prices. Everything's more expensive. We can't do it like we used to, but it's still the cheapest you're going to find anywhere. So be prepared and be on the lookout for that. And our speaker will be Dr. Krupp, the director of this place. And if you're not totally sick of Palomar yet, he's going to talk about the first astronomers of Palomar, which you heard. Yeah. And so when I get done with you, everything will be done. Steve Flanders told us how it was built, and he's going to tell us what it's doing. And Ed's going to tell us what it used to do, and weather permitting, we'll be there next Saturday.
Okay. Well, if there isn't any questions, we can just jump right into having you start your talk.
So Daryl,
Yes.
this is Spencer. I just posted the link for the nominations in the chat. So
Okay. So everyone online can see that, and
And drawing, make sure Spencer puts up.
and if somebody wants to do a nomination here, I guess I can accept that and write it down.
anybody want to nominate anybody?
Hold on. Microphone.
It's on.
I think Spencer sends out an information with a little synopsis of each candidate.
I'll nominate for the board Chris Burke and Victoria Fegan.
Who was the first one?
Chris Burke.
Chris Burke.
Mhm.
And Victoria Fagan?
Mhm.
Okay. So nominated.
I like the official way in which you do that.
Supposed to be, huh? Anything else? Okay, well, cool. Do you want to do an official announcement? We're almost halfway there, but come on up and talk to, bring the microphone. He knows how to introduce you way better than I do.
That's what you want. You gotta be explicit about what you want.
I'm sorry.
Put on my hat and look LAASE.
And you want to swap after that so we have the mic, or do you care?
I'll just use this one. You give that one to Andy. He's gonna need it. Here I am again. You've seen me before. I'm going to introduce tonight's speaker, and I'm not going to take all night doing it. Andy Boden is the Deputy Director of Optical Astronomy at Caltech and a whole bunch of other things, but basically he kind of runs Palomar Observatory, whether he likes to hear me say that or not. And last I heard, has an adjunct professorship at Georgia State University, and is associated with the Chara Array. Yeah, hey. And he's been associated with the Chara Array. He's an interferometer guy, and he once made the mistake of giving a talk about interferometry in front of me, and I've been harassing him about what photons are ever since. But, Steve Flanders told us how Palomar was built, and he's going to tell us what it's doing and what its future is going to be. Those of you who signed up for it are going to go. Hopefully, weather permitting, we'll have to look into that for the tour next Saturday. There's always a possibility that we won't be able to do it because of the weather. Keep an eye on that, but hopefully bring an umbrella or something if you come. And then, of course, for the annual banquet, Dr. Krupp is going to tell us about all the ancient people who were up there doing astronomy way before we did. So you're going to know everything there is to know about Palomar. And to introduce you to everything there is to know about Palomar, Andy, you're on.
Okay, thank you very much, Tim, for that well-researched introduction. I like that, that's good. So tonight I'm going to talk about one of my favorite places. I'm Andy, and so we're on a first name basis. And I'm going to tell you about one of my favorite places in the whole world, a place that I grew up dreaming about and ended up serving in a position of stewardship for. So this is Palomar Observatory. I bet you've heard of it, but in case you haven't, I'm going to cover the basics. So this is going to be an outline of my talk today, or this evening. And I'm going to spend about half the time talking about historical accomplishments, and the second half talking about what have you done lately. And so, in case anybody doesn't know where Palomar is in relation to San Diego and Los Angeles, we're right here in inland northern San Diego County. I can't really do a Palomar talk without mentioning at least Mount Wilson. It sounds like some of you have heard of Mount Wilson. Of course, it really is the framing context for all of Southern California astronomy, and I'm getting a little feedback if I stand here, so I'm going to stand over here. All of Southern California astronomy, and one would argue all of 20th century astronomy. And so you can see a picture of kind of a panorama of Mount Wilson on the left side. On the right side, I'm not showing you a picture of the Hooker telescope. I'm instead showing you a picture of a model of the Hooker telescope that's at Carnegie Observatories of Washington on Santa Barbara Street in Pasadena. And of course I'm going to show you this because there's something weird on the front of this model. And maybe if we get to it at the end of the talk and in questions and answers, we can make Tim tell us all about what that thing is on the front of the telescope.
Thank you.
You're welcome. So when Tim's been very kind. He's asked me to speak a couple of times, and he's done me so many favors over the years. I finally succumbed and said, yes, I'm going to do it. And as I started to think about what I wanted to say, I tried to think, what were the animating questions? And this is the 75th birthday year for Palomar, so I figured it's probably reasonable to take stock of what the observatory has done and frame that in terms of questions. So why are we saying 75? The dedication day for the Hale telescope was 3 June 1948. Here is a picture from the observing floor. And there's Leader Bridge up on the podium saying eloquent things about dedicating the telescope to Hale's memory. And then not long after that, the 48-inch Schmidt telescope, since become the Samuel Ocean telescope, it saw first light in September 1948. So when I was trying to think about questions, that would frame the talk. First one I came up with is Palomar is 75, who cares? Which is maybe a little rude, but it's a reasonable question. But when I started to think a little more about what I wanted to say, I came down to the question I'm asking myself, what is it that makes a 75-year-old observatory or an institution still relevant? And I think that's the question I'm going to try to take on today. And I'll eventually get to this third form when I'm trying to lay out what that relevance actually looks like. So the very first thing that I would call your attention to is that we're just cuter. We are very photogenic. Here is a panorama of the observatory. Of course, the landscape is dominated by the large dome of the Hale telescope, and for those of you who haven't been there, it's pretty large. We can talk in terms of numbers, but it's big. But it is the centerpiece of the compound. But in addition to the Hale telescope, we've got the 48-inch Schmidt over here. We've got the 60-inch telescope. The first telescope on site was the 18-inch dome. It's no longer there, it's in my museum. But we also have other telescopes on site and doing small, interesting, novel experiments. Of course, there's more photogenic things to show. So this is one of my favorite pictures of the Schmidt dome with a big tree in the front and Orion in the back. This, of course, is the Hale telescope, which, if you haven't seen it, it's big. It's about 530 tons of moving mass. And this is the same kind of upward perspective of the Hale dome that I showed in my title slide. An inception timeline looks like this. And it turns out that Palomar's inception and Griffith Observatory's inception are essentially inseparable. They happen together with many of the same cast of characters involved. So laying it out here, in 28, Hale secured the $6 million grant from the Rockefeller Foundation to fund the Palomar and the 200-inch construction. Now, the money for this place, Griffith Observatory, had been donated a long time before, but not long after that initial gift, by 1930, the trust for Griffith was ready to commit to building the place that we're in now. So that happened in 1930, and Hale, George Hale, I'll tell you about him in a second, was among the advisors that were chosen to help set the stage for Griffith Observatory. Now, in 1931, one of our staff members at Caltech, Russell Porter, became involved not just in Palomar's architecture, but also Griffith's architecture. And that's actually why that one individual, Russell Porter, is why these two institutions ended up growing up together and being very influential on each other. By 1935, Griffith Observatory was dedicated. And by 1938, the 200-inch dome was the first large building on site at Palomar. It was essentially completed and ready for the telescope to arrive. And it started arriving. Unfortunately, the world got busy doing something else between 1939 and 1945. And so a lot of things were put on the shelf. And it was another 10 years before the Hale telescope was dedicated and the 48-inch telescope saw first light. And from 1950 to 1990, well, the way we like to think of it at Caltech, of course, that's a little myopic, but if it was happening in global astronomy, it was happening at Palomar. Of course, that's not true, but it's what we say. Now, you can't give a talk about Mount Wilson or Palomar without having the obligatory slide about George Ellery Hale. So I'm assuming everybody knows this. I'll go through it quickly. Hale was essentially the patron saint of big telescopes. He built the world's largest telescope 4 separate times, including posthumously the Hale telescope. And it was him that secured the funding grant for Palomar Observatory from the Rockefeller Foundation in 1928. Our joke at Caltech is that the two most important astronomical discoveries of the 20th century were Hubble's discovery of cosmic expansion and Hale's discovery of fundraising. And that's really true. I never met the man. Obviously, a very influential and persuasive individual. He talked people out of disposable income quite frequently, including the Rockefeller Foundation. So we'd like to say that the 200-inch Hale telescope was the animating vision for the creation of Palomar Observatory, and Hale was that visionary. Palomar was developed against the economic backdrop of the Great Depression. You might have noticed the coincidence between when we received the grant and when the stock market crashed within roughly a year afterwards. And it turns out that that economic context really framed how a lot of the observatory was developed. The Depression-era economics really, well, there was a deflationary pressure on both labor costs and materials. And that really made that $6 million grant go a little further than it would have gone otherwise. But what it also did, and I think this is an important point that not many people mention, it created the context for a very large segment of human capital to join the project. People were looking for something to do. And so we were very lucky in developing the observatory that there were roughly 100 families that essentially relocated to the site and devoted their lives for something like 6 or 8 years to developing the site. So it was a really critical contribution from people who were economically displaced by the Depression and found an opportunity working with us. So not long after the dedication of the Hale telescope, science started. And if you were to ask me what are the first important results with the Hale telescope, I would point you to programs by this guy, Alan Sandage, who's very photogenic, standing on the catwalk level in the 200-inch dome. And he was a student of Hubble's, and he took up the work of cosmic expansion and looking at the isotropy and linearity of cosmic expansion. So if you think of cosmic expansion as something discovered by Hubble and Lemaitre, then it was really Sandage that turned that into an observational cosmology, the way we like to think about it in modern times, seeing that the expansion of the universe was very linear and isotropic over the range that he was able to probe. And back in '58, he actually published the first, what we think of as the first modern value for the Hubble parameter. You'll note I didn't say Hubble constant because there's, of course, tension in present day about what the Hubble parameter value is. But that's very different from the number that Hubble came up with, but it's actually fairly close to the modern consensus of the value of the parameter in the local universe. The other thing that was prominent in the first decade of the telescope's operation was the program of Jesse Greenstein. So Greenstein is the patriarch of Caltech astronomy. We literally didn't have an astronomy department before we built the observatory, and Greenstein was brought in to really help get that started. He was interested in using spectroscopic techniques that were made possible by the large collecting area of the Hale telescope to look at the elemental abundances in stars in our local neighborhood. And he did that for about a decade, and then this happened.
It is widely believed there is no more profound discovery of 20th century science than the realization that our world's chemistry is created by nuclear processes in stars. The air we breathe, the ground we walk on, the food we eat, and our bodies themselves all are based in elements forged in the hearts of stars. And Palomar was central to this realization. Up until the 1940s, the origin of elements in our periodic table was mysterious. English astronomer Fred Hoyle had the provocative insight that stellar interiors could be hot and dense enough to create elements heavier than helium through nuclear fusion, but the suggestion was hard to verify. Stellar elemental abundance studies using spectroscopic methods were just becoming possible as the Palomar Hale telescope began operations, and Caltech astronomer Jesse Greenstein used the Hale to study the chemistry of nearby stars. Combined with similar observations made by other researchers, patterns emerged in the abundance data that allowed Hoyle and collaborators to develop a robust theory of what we know today as stellar nucleosynthesis. In 1957, the team of Margaret Burbage, Geoffrey Burbage, husband and wife, Hoyle, and William Fowler published the seminal paper that gave a convincing outline of how stars create the elements of the periodic table in their observed amounts. In scientific circles, the team and their research became so widely celebrated that we refer to them both by a modern-sounding acronym of their names, B²FH. Today we understand the life cycle of matter on Earth as originating in the cores of previous generations of stars that enriched the galaxy with heavy elements created over their lifetimes. Sometimes the enrichment happens spectacularly in the supernova explosions of high-mass stars, and sometimes more gently when low-mass stars like our Sun lose their outer layers in the late stages of their lives. These processed materials become mixed with interstellar gas that eventually form subsequent generations of stars and their planets. This process continues today, with astronomers using Palomar telescopes to discover hundreds of supernovae each year and to study nearby star formation. We owe our very existence to this program of cosmic recycling, and it is both wondrous and humbling to contemplate humankind's deep connection to the stars that light our night and our day.
Excellent. The lights are coordinated. So along this same time, another important thread of Hale telescope science emerged. And I'm going to tell you about that next.
Earth orbits a fairly ordinary star, one of roughly 300 billion stars in our cosmic home, the Milky Way galaxy. The Milky Way is one of roughly 100 billion galaxies in the observable universe. Astronomers believe that all massive galaxies have supermassive black holes at their centers. The Milky Way is no exception, and the black hole at the center of the Milky Way is thought to have a mass of 4 million solar masses. The observations that put us on a path to this understanding were made at Palomar with the Hale telescope. In 1963, Caltech astronomers Martin Schmidt, Jesse Greenstein, and Bev Oak were studying a new class of mysterious objects called quasars. Schmidt measured the first optical spectrum of a quasar known to us as 3C273 using the prime focus spectrograph on the Hale telescope. While there were prominent spectral features in the data, they occurred at unexpected wavelengths that did not correspond to known stellar spectral lines. Soon Schmidt realized the spectral features he had measured were common lines of hydrogen, oxygen, and magnesium, but were redshifted away from their rest wavelengths, indicating a recession speed of nearly 50,000 kilometers a second. This recession speed implied that the source was at great distance, billions of light years, and the source must be tremendously luminous, trillions of times more luminous than the Sun. Today we understand quasars like 3C273 as examples of so-called active galactic nuclei that release tremendous energies during the ingestion of matter by supermassive black holes at their centers. Roughly 5% of all galaxies exhibit AGN behavior, and in 1978, Caltech astronomers Wal Sargent and Peter Young, using the Hale, found dynamical evidence of the very high masses driving these AGN, millions to billions of times the mass of the Sun. Their method measured the range of stellar speeds found in the centers of galaxies, so-called velocity dispersion. Applying the same method to normal galaxies like our own, they too showed evidence for massive objects at their centers. Essentially all massive galaxies have these central black holes, and a census of galaxy properties indicate that central mass is correlated with both velocity dispersion and brightness. Central black holes appear to be important in galaxy formation and evolution. The center of our galaxy is close enough that we can observe the orbits of individual stars, and the inferred orbits indicate that the central black hole has a mass of 4 million solar masses. While impressive, the Milky Way's central black hole is modest in size compared with some. For example, the black hole recently imaged in the core of the giant elliptical galaxy Messier 87 is thought to be roughly 1,000 times more massive, approximately 5 billion solar masses. It is clear that the pervasive presence of these black holes is not just an oddity. but an important part of structure formation in our universe.
So I know what you're thinking. You're thinking, where did they find this amazing voice talent? I can tell you he worked cheap. But seriously, my kids want me to allow comments on these videos on YouTube. I'm frightened to imagine what that would result in. But perhaps something that might come up a little more seriously, there's actually a very recent result from James Webb that bears on some of these questions. If somebody wants to ask me about UHC number 1, UHC1 in the Q&A period. All right, I want to drop back for just a second, and I'm going to mention a second discovery engine at Palomar. So Palomar was more than just the Hale. It was also the 48-inch Schmidt telescope. Of course, you're probably familiar with the big picture outside. And it was essentially a wide field survey or reconnaissance telescope. It was added as an afterthought. The idea for it emerged after the grant had been let and after things were proceeding along in the construction of the Hale. It was suggested by Walter Boden and Fritz Zwicky. And Hale liked the idea. He approved the construction of a prototype, the 18-inch Palomar Schmidt telescope, which saw first light in September 1936. And that went so well that by later that year, the Observatory Council was already scheming to imagine adding the 48-inch Schmidt to the Palomar portfolio. And as I mentioned a couple of times, this telescope saw first light in September 1948.
The Samuel Ocean Telescope, originally the Palomar 48-inch telescope, is a special-purpose device designed and built to add broad reconnaissance capabilities to the Palomar Observatory portfolio. Compared with the Hale telescope, which excels at detailed study of individual objects and systems, the Ocean Telescope's strength is surveying large segments of the sky efficiently. The telescope was dedicated as the Samuel Ocean Telescope in 1987. As originally conceived, Palomar Observatory was to be focused solely on the Hale telescope. The idea of broad reconnaissance in general, and the ocean in particular, was an afterthought suggested by astronomers Walter Boden and Fritz Zwicky. The ocean is a so-called Schmidt telescope or camera that delivers a usable field of view hundreds of times larger than that of the Hale. The Schmidt concept was first demonstrated on sky at Palomar in 1936 with an 18-inch Schmidt telescope, currently on exhibit in the Visitor Center. Performance of the 18-inch was so promising that Caltech committed to building the ocean in the late 1930s, and the telescope saw first light in September 1948. The ocean is famous in astronomy for enabling many sky surveys. Notable among them are the Palomar sky surveys in two different instances in the 1950s and the 1990s. Insights from these surveys have touched all areas of astronomy, from solar system dynamics to study of galaxy clusters, the largest bound structures in the universe. Discoveries made with the ocean famously led to the reclassification of Pluto as a dwarf planet in 2006. Throughout most of its history, the ocean used photographic techniques, glass plates with photographic emulsions that would be exposed and developed to produce images. However, over the last 2 decades, the ocean has been fitted with increasingly capable electronic cameras. Modern electronic detectors are much more light-sensitive than photographic emulsions. In present day, the ocean hosts a 600 megapixel camera and is the discovery engine for the Zwicky Transient Facility. The ocean operates purely robotically. There are typically no astronomers or staff present in the dome during observations, but instead the data are linked around the world in near real time.
Okay, shifting gears just a little bit. Palomar has had a significant history of architectural and artistic contributions. And that's really where Palomar and Griffith's history touch on each other. They both grew up in the Art Deco explosion period in LA County. So the early 30s, where Art Deco was highly prevalent, is basically the origin or the genesis of a lot of the architectural ideas that end up getting incorporated here and at Palomar. And that's really the work of that one individual I mentioned before, Russell Porter. You might also recognize these. So these are the famous Porter cutaway drawings. So if you haven't seen them, they're a series of about 25 drawings that Mr. Porter made between 1937 and his passing in 1947. And they basically depict essentially all of the scenes from the then conceived observatory, starting with this one up here and ending up in the war years with a pastel of the dome down here. The technique was basically pencil and ink on artboards. And he essentially at that point mastered a technique of being able to cut away and show the structure and the function of his subjects, which were usually elements of the telescope or the domes. And these caught on very quickly. They were incorporated in the decoration of Caltech astronomy almost immediately, and they eventually ended up being sold in these collections, which are presently out of print, but there are books that you can still find on used bookstores and online of these collections of Porter drawings. In addition, Palomar was surprisingly influential in popular culture. It somehow managed to, find its way into a lot of what was going on during the period. So it ended up getting captured in a lot of magazines, print magazines. And even advertising. So a lot of advertisers found themselves interested in associating themselves with the project. And my favorite is coming up here right at the end. Not the Viceroy, but the bread. Not certain what bread has to do with big telescopes, but there you go. But there was something about the combination of the era and the location and the project, a big shiny new telescope, that made advertisers interested. I apologize, I have one more video here, and we didn't manage to quite get all the permissions set up. You'll just have to take my word for it. There's some fun videos here of Palomar appearing in cartoons. My favorite one being Bugs Bunny arriving on a spaceship from Mars at the location of the observatory. I can't tell you why, but Palomar found itself deeply seated in the consciousness of the 40s, 50s, and 60s, and even into the 70s. So this is a good time to take a break. We've been talking about some of the history. I'm wondering if there's any questions at this point.
I have one question from the chat, which is...
yeah, UHC1. Let's say that till the end.
Okay.
It's an incredibly important result if it's true.
I understand that the 48 inches being used as like a finder scope. There's 500,000 pictures it takes every couple of hours, and then they superimpose again, and then they find something. That's when they send it to the 200 inch. Is that correct?
That's right. You're stealing my thunder from a little later in the talk, but that's absolutely true. So we're going to talk about that in just a bit. All right.
I have a question about the field of view. When they put the newer and newer chips on, the chips get a whole lot larger. So does something have to happen to change the field of view of the telescope?
So I think you're talking about the 48 inch. Yeah. It turns out that in its original format, there's basically a 14-inch square photographic plate. That's the usable field, and that covers about 45 square degrees or 48 square degrees on the sky with the 48-inch telescope, the Ocean telescope. It took us 20 years to be able to afford enough detectors to cover that full surface. So when we started, it was a much smaller field. It's really only in the last 5 years we've had enough money, thank you to the US taxpayer and the National Science Foundation, to be able to afford an electronic camera that could really service that entire field.
Right, okay, I get it.
Yeah. Okay, so one might reasonably ask, you've talked a lot of history, what have you done lately? So I realize I haven't actually listed the assets. Here are the assets here. The ones that are in bold print are actually in service tonight at the observatory. So the Hale, the 48-inch, the 60-inch telescope, I haven't talked much about it, but I will coming up. And then these 3 smaller experiments, which are more specialized and are really geared towards unique kind of niche, if you will, science. And I'll mention these 2 down at the bottom only because they're kind of distinguished alumni. We've talked about the 18-inch Schmidt and the Palomar testbed interferometer. As Tim alluded to, that's where I misspent a lot of my youth at Palomar, but it was fun, good, clean, geeky fun. But this is kind of a list of our assets. And this slide touches on who uses Palomar. So we run 365 nights a year. Why do we do it? Who do we do it? On whose behalf do we do it? So this is basically a list of the various institutions that are invested in the observatory. For the 200-inch, it's largely a collaboration between Caltech, JPL, Yale, and the National Astronomical Observatories of China. On the Samuel Ocean and the 60-inch, 80% of the time goes to an experiment I'm going to talk about, actually what this gentleman was talking about a few moments ago, called the Zwicky Transient Facility. It's basically an integrated experiment that looks for transients and then services them vectors them to other telescopes for follow-up. Winter is a new capability coming online. It's a 50-50 Caltech-MIT partnership, and it's looking for infrared transients. So instead of looking in the optical, it's looking for sources that change in brightness or position in the infrared. And there are reasons to think there might be unique populations you might find to look in that area. Flarescope is a kind of a fun, small experiment that's designed to look at low mass nearby stars in both the optical and the radio up at Owens Valley simultaneously to see if you can correlate emission in the radio and in the optical from flares that are often emitted by low mass stars. So I think the bottom line here with the slide is that Palomar is used by a broad international coalition and is surprisingly still has a global footprint, quite remarkably. Who operates Palomar? Well, Caltech owns it and operates it on behalf of the astronomers I just told you about. The observatory has a staff of about 30 individuals split between the compound. 25 people are on the serve on the compound, running the 24/7 operation. And 5 of us are back at the Caltech, the home office, the Caltech campus, and provide support. We have an active public engagement program. This is something that's important for the observatory. Pre-pandemic, we estimated that Palomar had about 75,000 visitors a year. And since the mid-2000s, we've had a program hosting weekend public tours given by a very dedicated group of docents, much like Mount Wilson. And these docents are very generous with their time. They contribute roughly 2,000 person-hours a year to make the Hale Dome accessible to the visiting public. We also have an active digital, if you will, engagement program. We have extensive virtual tour content. Maybe if we have some time at the end, I can show you some of that. We have services for people who visit and self-guide their tours. Those videos that you saw were taken from our self-guided tour package. It was a good pandemic-era project when you were stuck at home recording these things. And we have extensive media holdings and a YouTube channel. We also target outreach to underserved communities, and you were mentioning an upcoming event with Ed. So among our points of emphasis are targeting underserved communities and underrepresented groups. And for us, that ends up looking like our Native American neighbors around the observatory. So the Luiseño and the Juaneño bands are our neighbors, largely down at the observatory. And we've had an excellent partnership with those bands over the last few years. We started back in the early 2000s working with them, naming objects, naming discoveries in conjunction with them. This most recently happened in 2022, and we actually had the band up to celebrate the discovery of a new class of asteroids that was discovered at Palomar telescopes. It has this name that I would embarrass myself if I tried to pronounce, but it basically translates to Venus Girl. It's the first of a class of asteroids that were discovered orbiting entirely inside the orbit of Venus. And you mentioned Ed. Just this month, we released a new digital exhibit, The First Palomar Astronomers, which is an extension of the work that Ed started back in the early 90s. So looking forward and asking questions of relevance. Since the early 90s, bigger glass has been available. For 40 years, the Hale telescope was the largest effective telescope on the planet. But that all changed, of course, when the Kecks and the Geminis and the VLTs and the MMTs and ALMA came on. And they become increasingly accessible to astronomers worldwide at better astronomical sites. At the same time, space-based astronomy has become a big thing. And so it's against that subtext one has to ask, all right, so what are we doing at Palomar that continues to be relevant? What service missions and research programs are viable for the 75-year-old observatory? Our strategy, I think, can be summarized in these 4 bullet points. First, one never stops innovating. One has to continue to add new instrumentation to these telescopes in order to keep them productive and relevant. The moment you stop, you doom them to obsolescence. Second, one has to be fairly entrepreneurial in finding relevant problems where Palomar advantages can create leverage. So you're not going to tackle the deepest, highest Z astronomy that people are doing the 10-meter Kecks. One has to be a little more clever and think about what problems are accessible to what you have. We try to create educational opportunities. Caltech is still an educational institution. We still think of ourselves as if not the preeminent trainer of observational astronomy in the country. And so continuing to provide that access to astronomy graduate students and postdocs is a critical part of our mission. And then finally, engaging the public and sharing our worldview, which is to say, you know, it's fine to theorize, but at the end, data is the final arbiter. So, among the things that we're doing today. So, we're replacing instrumentation. I'll show you a couple slides on instrumentation. So, in conjunction with NAOC, the National Astronomical Observatories of China, we're building a next-generation spectrograph to go on the Hale with US national support. Thank you very much. It's a significant enhancement, both in terms of spectroscopic throughput, so light that actually makes it from the sky down to the detector, and in terms of temporal throughput, because we're building a great deal of automation into the observation sequence. So in theory, when this is commissioned and running well, you can set up an observing queue and then go back to the monastery and have night lunch. Really. And that we're looking at commissioning that capability in 2024. Now, this is what the gentleman was asking me about up on top. The Zwicky Transient Facility is kind of the end of an arc of transient astronomy experiments that have been going on at Palomar for the last 10 years. And we think of them as a vertically integrated experiment that takes advantage of all the telescopes on site to do what it does. So in this construction, the Samuel Ocean Telescope is the discovery engine. It does the automated scanning of the sky, just as the gentleman was asking me about. And that data is downloaded in near real time to Pasadena, where interesting sources that are changing in brightness or position are flagged, and those sources are vectored over for quick robotic follow-up with the 60-inch telescope. It's got a low dispersion integral field spectrograph, so quick low dispersion spectra to get a quick kind of triage classification on the objects that are being detected with the Zwicky. And then when, and then every so often with a regular cadence, we have dedicated observing runs on the Hale and on the Kex to do higher dispersion spectroscopy to really study and follow interesting sources. Key results, since June of 2018, we've got over 8,000 transients. 8,300 of them are actually supernova. A month ago, one of my colleagues, when we were in Wisconsin, one of my colleagues from UC I was having dinner with, and he was basically complaining to me because Zwicky Transient Facility has become the Costco of supernova science. We're putting everyone else out of business. They were unhappy about that. But it's a pretty remarkable testament to what one can do when we integrate these assets together and try to work on an accessible part of parameter space. This is my favorite. This will take a minute, so bear with me for a second. A project that's been on the Hale for the last 5 years is called the SAGA survey. So how many people here have heard of dark matter? Do you know what I mean when I say lambda CDM cosmology? He does. Anybody else? So, all right, that's one. All right, so CDM is cold dark matter. Lambda is cosmic expansion or dark energy, if you will. About 10 years ago, some theorists claimed that the Milky Way's population of dwarf galaxies was anomalous if you believed the predictions of lambda, the canonical lambda CDM cosmology. And this went by the name of the missing satellites problem, or if you will, the too big to fail problem. They're kind of the same thing. And so that inspired some observational astronomers, including my friend Marla Giha at Yale, to initiate a project called SAGA, which is really in the business of trying to take the census of the dwarf satellite populations around peer galaxies of the Milky Way. To answer the question, is the Milky Way common, usual, typical in its dwarf galaxy population, or is it atypical? So after 5 years using Hale spectroscopy and Keck spectroscopy, the initial results are in, and the Milky Way does indeed appear to have an atypical, as in too small, as in not as many, and not as much total mass as one would nominally expect, compared with other peer galaxies in the local universe. And this is a pretty remarkable result, framing how we think of these dwarf galaxy populations and how galaxies put themselves together. It's important to put the Milky Way in that larger context. I'm going to violate a dictum. Friends don't let friends show spectra in popular talks, but I'm going to break that here. So the other new instrument that we're putting on the Hale that I'll highlight is called PARVI. It's a radio velocity instrument. Most of the exoplanet work in California has gone to the Kex. We're trying to bring a little of it back to Palomar. We're doing that by using the adaptive optics system to inject light into the fiber, take it down into a laboratory in the basement of the Hale, a very carefully controlled, temperature-controlled area, so we can make a spectrometer very stable and inject a laser frequency comb beside the spectrum. And that laser frequency comb will be the velocity reference. So the objective with this experiment is to measure tens of centimeters of velocity precision in order to detect exoplanets around nearby stars. So we're trying to reach to that next level to be relevant in the exoplanet discovery space. And the last one I'm going to show you is this one.
In our everyday lives on the ground, we use optical fibers for really high-speed communication, and that capability has been adapted for use in space near Earth. DSOC stands for Deep Space Optical Communications, which is using lasers to communicate at high rate, and the application of that to deep space beyond the moon is what the DSOC project is about.
Primary objective is to give future NASA missions the tools for returning data at much higher rates.
The signals travel at the speed of light, so they come just as fast as they do for the microwaves, but you could send more data in the same time of a pass for the same spacecraft resources. The notion of being able to communicate, have video to astronauts on Mars is actually part of the vision that NASA has for optical communications. DSOC consists of a flight terminal that flies on the Psyche spacecraft, and then a ground network that has a station for transmitting up to the spacecraft and then receiving the laser signal down from the spacecraft.
Here we have to send a laser beam from Earth that the spacecraft has to receive, use as a pointing reference, and then initiate the communication link. So it's a very flight and ground joined at the hip kind of telecommunication system.
DSOC is being implemented as a technology demonstration to show that we know how to build terminals that can do this, with the idea that in the future they can be flown as part of the operational communication system on future missions. And we designed the terminal to operate out to about Mars' farthest distance, and Psyche on its cruise actually does a Mars flyby, so it's an excellent vehicle for the demonstration of deep space optical communication. DSOC is the first time that there'll be optical communication demonstrated beyond the moon.
The leap that DSOC is taking is huge. I can't express in words, what this will mean to actually see bits that were transmitted from deep space spacecraft received on the ground, and we can verify that, hey, we got the bits that you sent, here they are. Before that moment of elation and joy, there's a lot of work that we still need to do and think through.
And so this is a stepping stone for a future operational capability that NASA's committed to. There's a lot of activity in space and a lot of collaborative work that goes on, and it's very exciting to be part of.
So the really cool part here is that DSOC is on the telescope tonight. They're exercising their second pass opportunity because they were stopped last Monday night. And so I'm really looking forward to hearing the report tomorrow morning at how things went. So it would be unfair of me to just cheerlead and not point out some of the obvious challenges that lie ahead. Obviously, I've talked about the prevalence of space-based and larger astronomy assets that we have to compete against. And I've talked a little bit about how we've tried to position ourselves to be relevant and find niches where we can contribute, make significant contributions. And another key to that is to add innovative instrumentation and methods, including robotic telescope operation. 2 of our telescopes have no people in them. 3, actually 3 now. The humans are out of the loop, and they just kind of do their thing. And even robotic and AI-based methods for analyzing the data and bringing interesting objects to our attention. So you might have seen a Caltech press release a couple of months ago where ZTF had engaged in automated classification of supernova and picking out the ones that are the most interesting. So we're even moving into methods that get the astronomers out of the loop. It's probably more productive that way. Of course, the other elephant in the room, no offense to Mount Wilson, is Palomar is near 2 major metropolitan centers and 24 million people. And that means that issues of sky brightness are unavoidable. And what do we do about that? Well, we do actually have two things that we're kind of pursuing. Obviously, the science will not be as deep as it will be at the KEX, but we are looking at taking a greater fraction of our portfolio to the near infrared, where the atmosphere scatters less light, and the sky is actually darker. And the other project that we're pursuing uses adaptive optics to artificially create better seeing, and that results in less ambient light being scattered into the instrumentation. So here's my summary slide. I would argue that Palomar has been among the most culturally and scientifically impactful astronomy facilities of the past century. If my friend Tim weren't here, I might even say the most, but I wouldn't want to be rude. But I would suggest to you that Palomar has been more scientifically relevant in the last decade than it was in the previous decade. And that's a pretty remarkable thing to say for a 75-year-old facility. I admit we're a little proud of that fact. We do have, and we must maintain, a broad and targeted community engagement program, because among the key messages that we have in our legacy is one of inspiration. You know, we're attacking problems that we think are relevant, and we're attacking them in what we think are relevant ways. And we're hopeful that our community will be up to the challenge to remain relevant and inspirational for years to come. With that, I'll leave you with the stuff I didn't talk about on this slide, and thank you for your kind attention.
Remember, if you have questions in-house, the Zoomy people cannot hear you unless you talk into the microphone. But at the moment, since we already asked questions, I'm going to ask Spencer if there are any questions from the Zoom people online.
There are quite a few. Let's see. There's one that's about UHC1 that was early on.
Yeah. All right. So forgive me, I planted that question, but it's very important. So in the AGN video, I talked about the coincidence of supermassive black holes at the centers of all massive galaxies. It's really a chicken or egg problem that we've had for a long time. Did the black holes grow up together with the galaxies, or were they the nucleation sites for galaxy formation in the early universe? So a week ago today, there was a huge press release out of CFA at Harvard and in Nature Astronomy talking about an observation made with James Webb and Chandra, claiming a billion solar mass black hole observed in the early universe at Z of about 13, which is incredible if it's true, because it suggests that this kind of breaks that chicken and egg degeneracy, and it may in fact be these black holes that are forming early in the universe that serve as the nucleation sites for galaxy formation.
Unless you stand over by the podium, the people on Zoom can't see you.
Okay, so now I'm okay. Imagine I said all of that while I was here at the lectern. So does that answer your question?
I see
yes.
a question about Porter. Is it true that he worked only from blueprints to create his drawings?
Yeah, I didn't talk about that, but that's absolutely true. The first 6 or 8 of the giants of Palomar collection were drawn before anything was built. There was a building, but there was no telescope parts on site. And so this was all done from blueprints and spatial reasoning skills that Mr. Porter had. And I'll even add that before the 1937 and onward series, there was an earlier series of Porter cutaway drawings from 1934 where they were still debating what design the telescope would have. So there are actually some very early Porter drawings in this same style, which show Porter's amazing ability to visualize in advance of anything being built, anything being physical. So absolutely true.
Boy. And we're asked how much of the 48-inch Schmidt's field is aplanatic.
Ooh. So I'm going to interpret that in the context of image quality. So when does the image get worse than a certain standard? The sampling of the ZTF camera is gauged to be Nyquist sampled. I apologize if I speak in tongues for a second. To be Nyquist sampled for 2 arcseconds seeing. And I want to say that out to a field angle of about 6 degrees, we're well within that specification. So something like 85% of the 47 square degrees is well within that sampling spec. We do have some vignetting and we do have some coma that expresses itself in the corners of the field. But the vast majority of the field in both the Palomar sky surveys, photographically done, and in current day with the ZTF camera, are getting our specified, our anticipated image quality.
And there was somebody wants you to talk about protecting the 200-inch mirror from gunfire while it was being shipped.
Well, now this is California, not Texas. So I'm not aware of any gunplay that we've had at the observatory in the same way that they've had at McDonald Observatory. But I guess I don't have a better answer than just to refer to my friends from McDonald.
Nobody actually shot at it that I know of, but I know it was protected. So there you are.
Oh, I get it. I'm sorry. We're talking about when the mirror was transported.
Shipping, yeah.
Yeah, I'm sorry. Yes. I misunderstood the question. So when the mirror blank made its way from Corning, New York to Pasadena, it was shipped by rail, and there were steel plates added to protect the mirror because it was anticipated that people might take shots at the mirror. I'm not aware of anyone ever actually doing it, but it was a consideration.
Now, are there questions from the people sitting in the audience? Oh boy, there's a question. That looks like Victoria.
I have a couple. And that voice was yours, wasn't it?
It was.
I did have the thought before you said anything. That's a good voice. Okay.
You can pick up your check at the door.
Can you elaborate more on the temporal throwaway? Like,
I'm
was
sorry.
It light or?
It might have been. I don't know if there was a typo on my slide, but we're talking about throughput. So really just measuring more spectra per unit time. So I can't make my 200-inch telescope get to the faintest sources. But if I can optimize the optical throughput of the spectrograph and make the system as efficient in time as possible, then I can measure more spectra per unit time. So I've got less dead time. And the best way that we found to have less dead time is to get the astronomers out of the loop. Have them make their list of targets they'd like to service, and then let the machines take care of it.
AI. Okay, I'm just kidding. And then my other question, you were talking about, something you mentioned reminded me of the Gaia spaceship, the space telescope, the Gaia space, it's taking this really amazing picture. It took this amazing picture of the Milky Way, and the image you had on with all those images of all those galaxies, and the test you had someone run that just came back with some data. I was just wondering if how did we through that test find out how large our Milky Way was, and do you use Gaia information at all?
So I think you might be talking about Euclid, which is the new spacecraft with a wide field. I personally, I'm a walking, talking cliche. I'm an astronomer who studies stars. And so Gaia, the European astrometry mission, has been nothing short of, words, revolutionary undersells it. It's been this remarkable revelation in terms of galactic structure, in terms of understanding stellar populations. Basically, everything that we've always wanted to know about the galaxy, Gaia is teaching us. And it's been absolutely incredible. So the answer to your last question, do I use Gaia? Every day. It's absolutely incredible. It's an asset that, we could not have appreciated how revolutionary it would be until we saw the data. So, yeah, I have to, bow in the direction of the European Space Agency. It's been Hipparcos before it, and now Gaia have been truly revolutionary in terms of understanding of galactic structure.
Anybody else in the room?
Hi, I'm curious. AI was mentioned. I would love to hear what role machine learning models plays in image enhancement. Hi, right here.
Oh, I'm sorry. The glare from the lights. I'm going to step away so I'm not like in the Clegg lights. So I'm not aware of anybody who's using AI for image enhancement in astronomy, and that's more a statement of ignorance on my part. I'm just not plugged into that part of the technology. I'm certain it's happening. Obviously, it's happening in other contexts. Google is classifying your photographs from your phone using machine learning. But the kinds of things that are happening at Caltech are more in the processing of data. So the training sets of looking at spectra and saying, that's a ducky, that's a bunny, that's a horse with a hat on. Somebody up there probably gets that joke. But being able to understand what a spectra is telling us more rapidly than the human brain can handle. So a lot of what people are working on at Caltech are really processing that kind of data as opposed to necessarily enhancement of images.
So that it would be playing a different role.
Yeah, it's a complementary role though.
Really
Yeah, absolutely.
Data
Yeah.
and interpretation.
I'm certain people who do image analysis, and we mentioned Euclid just a moment ago, its science mission will be wide field imaging and looking at potential distortions in the image space because of mass distributions. And I'm certain that AI will play a huge role, because it's playing a huge role everywhere. I'm certain it will have a huge role to play there. I'm just not competent to speak to it.
Can you describe some details regarding the spectroscope, the grading, ruling engines, and so forth, the slits, all these things that go into a state-of-the-art spectrograph compared to things that I'm talking about?
Yeah. So yes, I can speak a little bit to that.
Would you please?
I will try. I'll do my best. So for us, if we're looking at pushing on throughput, the single biggest step forward that we're making with, say, the new optical spectrograph is we're moving away from mechanical gratings, so rules on a reflective surface, and we're moving into something called holographic gratings, VPHs. And we're doing that because they're much more efficient in terms of saving every photon. They're roughly a factor of 2 more efficient than your gratings. So we're using a different kind of grating, which is holographic. And it's more complicated to use because it doesn't disperse the light in the same way that a simple mechanical, a conventional optical grating does. But because the throughput is so much better, you're motivated to go to the extra trouble. For our infrared spectrograph, what's going on there is we're actually taking advantage of our adaptive optics system to inject the light into a single mode fiber. And that, you can think of that as an example where if I'm looking at a bright star, I can afford to get rid of the bad photons and keep the good ones. So if there are any electrical engineers out there in the audience, think about a waveguide that you're coupling a single mode into, and all of the other modes are rejected. They're evanescent. They don't propagate in the waveguide. That's what the single mode fiber does. And so what comes out the back end of the fiber is a very pristine phase front. And you can take advantage of that to really push and sample the spectra very finely. The infrared spectrograph I talked about has a dispersing power of R of 100,000. And of course that couples with the science it's trying to do. It's trying to measure very small changes in the Doppler motion of these stars to see if there are lower mass planets there. So those are two examples of things that we're doing very differently today than we were doing 3 decades ago.
Thank you.
You're welcome. Cool.
You wanted to ask another question?
Thank you. So I think I shouldn't have narrowed the question to image enhancement about using machine learning models, but I guess maybe just a general question: how is Caltech using machine learning models to with the data that's collected?
Well, the thing I'm most familiar with is the ZTF experiments and doing the automated classification of these transient spectra. That's been the prominent result that's come out in the last few months. But I know of some other Caltech researchers who are trying to use AI analysis, machine learning analysis of time series photometry in order to look for both stellar activity and the possibility of transits of planets in front of stars. And I mentioned, in fact, I've got some of that, well, maybe it's here, but there's that second bullet on that slide of the stuff I didn't talk about, but I could have, is exactly that stuff. We're actually doing measurements of planetary transits at the Hale with the objective of seeing if we can see various things, including the evaporation of the photospheres of the planets in a particular helium line at 10860, blah, blah, blah. Those are the kinds of things that I'm familiar with. I'm sure there are other things, and we just recently had a seminar at campus of a lady from the University of Texas who was doing simulations of and analyses of star-forming regions using machine learning. I can't tell you that I understood what the exact advantage was in the circumstance, but it sounded interesting.
There was a question online if there are plans to do yet another Palomar sky survey with the Schmidt.
Interesting question.
Sounds like a good idea to me.
It's not a crazy idea, is it? I mean, we spent $10 million developing this super sexy CCD camera. It seems to make sense to take advantage of it. I can't tell you that we're really sure what the future holds for the ZTF camera and the 48-inch Schmidt in the 5 to 10 year time frame. I'm certain that one component will be looking for light from gravitational wave sources, so-called multi-messenger astronomy. We are among the few facilities in the world that can do very rapid and very wide angle follow-up for sources that are detected with gravitational waves. And so that'll be kind of the bread and butter of what the 48-inch telescope will be doing over the next 5 years. And we are right in the middle of the next LIGO run, 04. They're actually in a down period, engineering period right now, but after the first of the year, they're expecting to ramp it back up. So we're hopeful that there will be some interesting results coming out about optical counterparts to gravitational wave sources, because that's a rich scientific field that we can imagine exploiting there. But beyond that, I don't know that I know we have a very clear sense of what we're doing.
Any other questions here?
I'll ask Tim a question.
Go ahead.
Explain the interferometer boom on the Hooker telescope.
I've been hoodwinked.
You have.
Yes, can you go back to the slide that
I can.
shows the
I can.
100-inch?
I will try.
It's there somewhere. I saw it.
Yep, I have it in the front of the talk. Of course, I can't actually drive the...
Well, the idea is there is a 20-foot steel beam across the top end of the 100-inch telescope, and it has a couple of mirrors on it that can move. And originally, they were moved by, your least favorite graduate student.
Or Francis Pease, as the case may be.
Yeah. Eventually, they put an electric motor on it, but I'm not familiar enough with the optics to describe why what you see is what you see, but there it is, the picture on the right. That's the model of the 100-inch, and right up at the top of the tube is the model of the 20-foot steel beam. But there are two sets of fringes that are visible in an eyepiece, and the astronomer looks through the eyepiece. One set of interference fringes does not move, the other one does. You move the mirrors back and forth until the moving set vanishes, and at that point, the two mirrors are separated by a distance that correlates to the angular size of the object you're looking at. And in this case, it was the very first angular diameter measurements ever made of a star. Basically, it's the birth of astronomical interferometry. They did it right, and that was Michelson and Pease, and I think they started near the end of 1919. And of course, the Chara array and the Keck interferometer and all the other big interferometers are descendants of what was done on the 100-inch. And of course, the Chara array currently is the largest of its kind in the world because everything at Mount Wilson was the biggest in the world. And that's a good explanation.
While you're on Chara, there was a question about how they keep the phase or something about when they add the seventh telescope at Chara.
I guess it
the
is.
hell out of me.
I don't know what the question is.
There's a seventh telescope. There's a seventh
Yeah, they're
telescope
adding a telescope,
The
right.
seventh telescope coming online that it's I guess, optically connected. And there was a question in the chat about how do you keep the phase and a second word that I can't remember. How do you keep that together with the other 6 telescopes? Because they're all, it's a different way to get the data.
To amplify, so my understanding is they're using fiber to do that. I understand how with the evacuated tubes for the current Chara, how you keep the phase and amplitude information. How do you do that with fibers?
So I'm going to speculate because I don't work at Chara and I don't play a Chara astronomer on TV. So I think the right answer is the same way. And let me elaborate on that just a little bit. So you're absolutely right. In the original design, Chara had 6 collecting apertures. All of the light came in to the combining area through free space propagation. It was in evacuated tubes, but it was free space propagation. And then you overlapped depending on which beam combiner was involved, you overlapped the pupils from the telescopes, or you overlap them at an image plane, depending on which combiner it was. So if you're propagating light from that 7th telescope in a fiber, it doesn't change the fundamental nature of the electromagnetic field that arrives at the combining area. So the simple answer, I think, which might not even be wrong, is, which is always good, is there will be some form of phase offset relative to the free space propagation, but if you can calibrate that, then you know where to look for the fringes of this 7th telescope in relation to the other 6. Now, I don't know, and I apologize, this is my own ignorance. I don't know what Char is doing in terms of adding 7-beam combination facility. Their existing 6-beam combiner, the Merck combiner, that used image plane combination, and you actually formed the fringes in various sets across an imaging detector. I don't know if they're imagining expanding that technique with the 7th telescope, or they're doing something different. But there's nothing intrinsically, you're not changing the physics whether you bring the light in free space propagation or in a fiber.
Sounded good? Yeah.
Full jaw.
Well, I think that's probably all we can do for questions, and we should move on to a raffle.
Yeah.
All right. Thank you again, everybody. Okay, I'm going to turn this off.
I would have to defer to him. I don't know.
I did.
Okay, for those of you online, I reposted the link for the raffle, and there are 24 people online, and only 14 have signed up for the raffle.
Let's give them a minute or two.
How many people are online?
Is there anybody in the room who didn't get a ticket?
Do we know what we have for prizes tonight?
Did you bring any lasers by any chance?
I don't know if Alicia's here, and I don't know if we have lasers.
I have lasers in the car. Thank you.
Alicia's online.
Alicia is online. Okay, good.
Did your son get one? For you? Is he here? He's got to be, right?
No, he did not get it.
Oh, here's 2 tickets. Go ahead.
Give him one too. What's that? Somebody hoarding tickets? What?
Yeah.
Oh, lost and found. Okay, so he's got one. All right, cool.
Thank you very much.
All right, I'm going to close out the online raffle in about 30 seconds.
Okay.
You all right?
Yeah, I'm fine. I'm running for the board, you can let people know. Yeah. When do we tell them? It just comes out on
Dave Yackerson said that he is.
I'm running on a board again.
He's going to run for the board member.
You can vote for me if you want.
So he's on the ballot. I'll be on the ballot. I'm president. I guess I could stay president.
Yeah.
Yeah, okay?
Yeah, absolutely.
The rush to fill your seat is overwhelming.
Yeah, yes, look at the line. Look at the line standing behind me to take the position. Isn't that fun? Yeah. Especially when they know what's going on. Isn't that fun?
Ready to go?
I don't know. Spencer, ready?
Spencer?
Hang on one second. Okay, let me grab the list of people who signed up online.
How are we doing this? You pick one off of the list. We pick one here.
Yeah.
Okay. You want me to do the online one first, or you want to do the? Okay.
Yeah,
Make screen share.
Let's see it there.
All right. Let's see. Okay, Dan Bernanski is the first one online.
Very cool. Thank you.
Yeah.
Okay. Got it.
Are we alternating? Do we know what he won?
Dan won Constellation drinking glasses. I was trying to make sure he hasn't won that before because I know he's won in the past. So
I have not.
okay.
Okay, in-house here, the number is 833-4742. 833. We got a winner up there. Did you win? Bring it down. I need to see the ticket. Cash it in. Especially this guy over here. 742. That's the last numbers. Okay, and we got to put his name down and or just tell Alicia, right, who it is? Okay, go ahead.
Mhm.
Yeah, if you could get the email address and you send that to Alicia.
Yeah, make sure it's right too. And they want a laser.
If you want a laser, I can deliver tonight. Is it a green laser? Your
Okay.
laser is different than our lasers? Alicia?
Huh?
Your
They should be all green. I only give out green. I mean, if I gave out the blue ones, then they would look like lightsabers. Those are really cool too, but I've been sticking with the green. If people want blue, they should just send a suggestion and I can do that too, but no, it should be the same.
Nah. I have them here tonight, so I can deliver that one. Okay, Spencer?
Okay.
Okay.
Let's see. Andrea Scarlett.
Andrea Scarlett is online. Okay.
All right, so Andrea won an item from the LAS store.
Okay, LAS store item. That's good.
All right, the next number in-house is 833-4738. Up there, okay. Come on down, we'll get your, Victoria, where's she at? She's right over here. Yeah, just go over there and she'll get your email. And what did this gentleman win?
He won the Eclipse book. It's America's First Great Eclipse, based in 1878 by Steve Ruskin. To celebrate the annular and total eclipses, I figured it'd be nice for people to read about eclipse history. So, yep.
Okay, cool.
Okay.
Next online.
Email and his name.
Is your turn, Spencer? We can do another one here.
Okay. This will be the final one. This is number 3, okay? Is 833. Oh, go ahead. What, okay, 833-4737. We got a winner. Okay, go let him give you your email and you're all set.
And what would he have won?
Laser.
Okay, I can deliver that tonight then. Cool.
Okay.
All right, so one more online, and we're good.
Oh, okay. We're only doing 6. Okay. Oops.
Do we have our
Spencer?
last winner? Can't see it. Who was the last winner there?
Okay, I'm sorry. Okay.
Dan Thompson? Is that right?
Hey, I'm sorry, guys. I just had an emergency phone call. Stan Thompson was the next one.
Okay. Stan Thompson won the Observer's Sky Atlas by Eric Kokoschka.
All right. Yeah, I did the announcements early. I did all those. All right, so well, I think we are done. 9:40. Okay, that gives us plenty of time to relax, maybe talk a little bit. We need to be out the door by 10. Okay, we need to be out the door by 10. So end of meeting officially, but we can hang for a few minutes just to make sure we're out of here by 10. Thanks, everybody. It was a fantastic talk. It was a fantastic talk. Thank you very much.
Somebody tell them to quit sharing the screen.
Sorry about that, guys. We just had my dog went in for emergency surgery, and that was the vet calling to say everything was okay.
Oh, that's good. I'm glad your dog's feeling better.
Yeah.
The people still online can hear it. We're going to have jackets available at the banquet. So if anyone's interested in getting an LAIS jacket, without the name, names are going to be no more names on the jackets, but we're going to have them available all the time.
Hey, Spencer, the meeting is over now.
Okay, great.